Thank you for the introduction, Mr. Professor Winter. My name is Birger Buschmann, and I'm going to present today the topic additive manufacturing of wood. Well, why additive manufacturing of wood? Worldwide, there are massive amounts of wood waste produced. Just in Europe, it's estimated that there are around 50 million tons produced yearly, with just around 40% being recycled. The rest is either incinerated or put on landfills. And with this recycling rate, we are actually one of the best, because in the US, for example, there's just a rate of 15%, and in other countries, the rate is even lower. So there's a huge resource potential, and we need new and innovative approaches to tap into this potential. Additive manufacturing can be one of those approaches. Additive manufacturing, or 3D printing, is a term for a certain set of manufacturing processes where, contrary to conventional subtractive processing, like milling, sawing, or drilling, material is incrementally added to create an object. Oops, das war zu falsch. And with this, basically no waste is created, because we are only using the material that we actually need for the fabrication of an object. But there's another even more important aspect. For additive manufacturing, we need tiny little particles, just what you can see here in the front of the picture. So with additive manufacturing, it's actually ideal to upcycle all this material to generate high quality products out of wood waste. Today, I'm going to present you the three main additive manufacturing process categories where wood is used as a feedstock material. Later on, I'm going to present another process that was here developed at our institute, and I'm going to go into the application of it, but just very briefly. Yeah, the first process category is binder jetting. Binder jetting works like this. Wood particles are layer-wise selectively bound together with a binder. By doing this multiple times on top of each other, objects are created. Possible binders can be either polymeric, like here for the pen holder in the first picture, or mineralic, like the one for the artwork here in the second picture. It is possible to create very delicate and geometrically complex parts with this process, but there is a drawback. The particle layer only has a density of around 50 to 60% of that of a single particle. This means that there are a lot of cavities in the material, and these cavities have to be filled by the very or relatively expensive binder. In addition to that, the mechanical properties of the parts produced with binder jetting are relatively low. So usually there is a very cost and time-intensive post-processing necessary to actually use those parts. The second process category is material extrusion. Here, viscous material is extruded out of a nozzle and deposited in strands on top of each other. This way, objects are created layer by layer. One very famous material extrusion process is fused filament fabrication. Everybody knows these little desktop printers that are in little workspaces. This is the technology that they're using. In this process, molten plastic is extruded out of the nozzle. To this plastic, one can add around, let's say, 20 to 30 mass% of wood particles. Any amount higher than that is usually clogging the nozzles and is leading to reduced mechanical properties. While this process is usually used for smaller parts, you can also really upscale it, like the University of Maine did here with their huge printer here. And they used the wood polymer composite to print the whole house. The drawback here is that obviously the polymer is not really economically feasible as a construction material. So this object here is more of a demonstrator object. A process with which significantly higher wood contents can be achieved is called liquid deposition modeling. It's also a material extrusion process. And here a wood paste is extruded out of the nozzle. The wood paste consists out of wood particles, a binder, and a liquefier. It is possible to create parts with over 85 mass% of wood with this process. The drawback here is that the liquefier, which is necessary to bring the material out of the nozzle, needs to evaporate to solidify the part. And this evaporation leads to voids in the material and in turn reduced mechanical properties. Because of that, there's currently not a real application for this process. It is investigated whether you can use this as a process for furniture, like you can see here in the second picture. There's also the idea of using it for individualized packaging material. And there's a company that wants to print tiny houses with it. How far they will come with that, we will have to see in the future. The last process category I want to present to you is sheet lamination. And here, thin sheets of wood material are cut into shape and then laminated on top of each other. While it is possible to create very high wood content and very high strength parts with this process, it lacks the main advantages of additive manufacturing. By cutting the sheets, waste is created, and we do need very specific and high quality wood products, namely the sheets, to make this process work. Nevertheless, it is possible to create connector elements like this one, and even replicas of churches, like you can see here in the second picture. Because of all these drawbacks, here in our institute, we developed a new process. The goal was to additively manufacture high wood content, high strength parts. We called it individual layer fabrication, or ELF, and it borrows aspects from both binder jetting and sheet lamination. My colleague has a demonstrator object that he will pass around. The basic scheme of the process goes like this. First, we scatter a thin layer of particles, and then on these particles, we selectively dispense, according to one slice of our object, adhesive. This is the binder jetting aspect of our process. Then we press the layer under heat. The heat is solidifying the adhesive, and the mechanical pressure is compacting the voids between the particles. This way we can really reduce the amount of necessary adhesive and increase the mechanical properties of the material. Finally, we remove the unbound particles and laminate the one layer on the stack of previously fabricated layers. This way we can create our objects. And as you can see here in this table, we are able, with more than 80 mass% of wood, to create really strong and durable, really strong and durable material. In this table, you see the average values of mechanical properties for a specific set of process parameters and material combination. So you should not look at this as absolute values, but more of an orientation. We are surpassing the properties necessary for plywoods, and we are going even into the direction of particle boards, and we are going even in the direction of plywood. And as you can see here in the last two columns, while we have very strong mechanical properties in the layers, perpendicular to it, the strength drops by a factor of 5 to 10. So this is really something you have to consider when you are designing objects that are to be produced with the ELF process. And one very helpful tool we have here is structure optimization. Structure optimization, very briefly summarized, is a design technology in which a computer generates the design of our desired object. In our case, we ask the computer to minimize the mass or the volume of the object under a certain load, while still complying to the design constraints. Because of because the computer-generated designs are oftentimes very complex, it's not really feasible to create these designs with conventional manufacturing methods. But with additive manufacturing, where complexity is basically free, it's very easy to create these designs. So both of these methods together are a perfect match. You can create mass minimized designs with only the material that you actually need. Here in this picture, you can see a 4-point flexural test specimen that was successfully designed with structure optimization and then finally fabricated with the ELF process. Another very interesting field of application is acoustics. In this picture, you can see a Helmholtz resonator. It's basically an airtight cavity with an opening of a defined length and diameter. As you can see in the diagram, this resonator is able to absorb a very specific frequency of sound. Now, by altering the geometry of the resonator, we can also change the frequency that is being absorbed. So one could imagine a whole wall or ceiling filled with those resonators, filtering out the unwanted sounds of, for example, lecture or concert halls. Finally, here's a picture of our most recent produced part. This is more of a aesthetic object, I would say, a little table. And I think this is also a possible field of application, looking into aesthetic or individualized furniture. That's the end of my presentation. I hope it was informative, and I'm looking forward to your questions.